Alrighty, guys, welcome back to Calc 2. Today, unfortunately, I'm coming to you via a pre-recorded lecture because I have jury duty today. So I am actually at the courthouse right now, but I'm going to do my best to deliver to you all of the material that you need for Power Series for section 11.9. We will wrap up anything that I don't do here today on Thursday. Of course, it's a big section, but let's go ahead and dive in. On my screen share here. I was actually just recording this a moment ago and my internet went out for like the millionth time today. It's been one of those days. Yeah, here we go. So this is MAC2312, section 004. It is a lecture. And today for you is the 13th of April, 2021. A few things today. We're going to talk about representing a function, representing functions as power series, which is section 11.9. And this is one of those trickier sections. So please pay careful attention, take very good notes. Before we get into that, I want to say this one thing, comment. The exam 2s are graded. My dog is looking at himself. Hamlet, be good, bud. The exams are graded. And they weren't bad. They were good. A note or two, I suppose, is in order here. So first, just because they were good, what I mean by that is that the scores were statistically in line with what I expect. Not like everybody got an A, unfortunately. But the distribution looked how it should. The average was where it should be. The histogram has the shape that I've come to expect from many years of this class, which means that, you know, I think for the most part, people are working as they normally do. We're kind of getting into the swing of this. And also that most people are, for the most part, representing their knowledge honestly. There are one or two things that I noticed in there that were a little bit suspicious or a little bit weird. And I just want to say, just because you're not getting strung up and caught doesn't mean that I don't know something weird is going on. I know that most of you did everything exactly right and were honest, so I'm not going to harp on this for very long. But if you didn't, just be aware that I'm aware, and I'll be trying to figure out what to do here over the next few days. But yeah, that's it. The distribution was good. Grades are in. Please look at the comments. It's very important you read the comments I wrote, both in the test itself and on the written work. They're separate files. They have separate comments. I can annotate the written work, which is nice. But I also leave shorter comments. I leave shorter comments within the test itself. So please look at both. There's plenty of things that need improvement, a lot of algebra mistakes, things like that. But overall, the results were as expected. All right. The content for today is representing functions of power series. So the main question we're trying to answer is given a function f of x and a number and a choice for the center, number A, can we find a power series? Can we find power series sigma n from 0 to infinity Cn times x minus a to the n with that center, which converges to the function f, at least on the interval of convergence, right? At least for those x values where the series does converge. Can we find a series so that when you plug in any x value from the IOC, you get what you would have gotten if you just plugged into f? That's the game. And that's why we call it a representation. Another word for this is a power series expansion for f of x. So again, what we mean by this is i.e. A series satisfying sigma n from 0 to infinity Cn x minus a to the n. That is straight up equal to f of x, at least for all x in the IOC, interval of convergence for that series. That's the idea. And the easiest place to begin this discussion is with the example that we have, right? So remember, every power series has some set on which it will converge, meaning some collection of x values such that when you plug in those x values, the series is a convergent series. And it's always a set symmetric about the center. So that number a, I'll go through an example here in a minute, but we want to find the series that gives you the same outputs, right? The sum of the series is the same as the function value would be if you plug that same number x in. So the example we've seen before is consider the function defined by the power series f of x equals sigma n from 0 to infinity x to the n. Which is, in signal notation, it looks like that. If you write it out long form, it's 1 plus x squared plus x cubed and so on. I just want to begin by thinking about this series, this power series. We know, because this is a geometric series, by a geometric series, the results developed in 11.2, we know this series will converge. It is a geometric series. The sum is just a bunch of stuff to the n. So we know it will converge provided the common ratio, which in this case is the absolute value of the common ratio, which in this case is the absolute value of x because x is the common ratio, is less than 1. So the IOC for this series is the solution to this inequality, which is -1 is less than x is less than 1. That's the open interval from -1 to 1. You can test the endpoints when you plug in either endpoint, the series diverges. So the IOC really is that. If you draw it out, it looks like this. Right, the center here is 0 because x to the n is x minus 0 to the n. And you can walk left or right 1 unit and stay within this IOC. So when we draw out the IOC, that's what it looks like. That means our radius of convergence is, remember, this distance, which here is 1. Sorry, my dog. Nova. All right, so remember, this is just what we mean by an IOC. It's the set of all x's such that when you plug those x's in, the series is a convergent series. But more than that, more than this, we know what this series sums to. Also, by the formula in 11.2, we know the sum of this series. The sum of sigma n from 0 to infinity of x to the n it's 1 over 1 minus x. Thus, for x's in the interval -1 to 1, we have sigma n from 0 to infinity of x to the n, that's my function f of x, is actually equal to 1 over 1 minus x. We talked about what this looks like last time. You can look at the partial sums of this series as graphs, right? Each partial sum here is a polynomial. And if you graph more and more and more of those partial sums, the graph gets closer and closer and closer to the graph of 1 over 1 minus x. We saw this last time. This is sort of the basis for everything we're going to do with power series in section 11.9. I'm going to rewrite this. So this is our first function representation as a power series, right? If you have 1 over 1 minus x, you can represent it or expand it, either word you want to use, as sigma n from 0 to infinity, x to the n. I call this the geometric series trick. And I'm going to rewrite it in terms of the variable u, because our goal here is to find representations for other functions. So we'll be substituting different things in for u. So this is the geometric series trick, and it is the holy grail for section 11.9. It says that 1 over 1 minus u is equal to sigma n from 0 to infinity u to the n. And this is true provided the absolute value of u is strictly less than 1. So tuck this in your pocket, never forget it. It's the most important power series in the land, right up there with the other important series we will learn in the next section. So how do we use this? How do we use this? Well, suppose I wanted to find a power series for f of x equals 1 over 1 plus x squared. The game is to take your function, whatever you're given, and rewrite it to look like this. Because once you have it in the form 1 over 1 minus u, 1 over 1 minus something, you can write that as sigma n from 0 to infinity, that something to the n. So if I can rewrite this function to look like 1 over 1 minus u for some expression u, depending on x, then I can get that function as a power series. Here, we use the geometric series trick. I'm going to use this trick by saying f of x is 1 over 1 plus x squared, which is the same as 1 over 1 minus the negative of x squared. Now you want to add something that's the same as subtracting the negative of that thing. Very simple algebra move. A little sneaky, maybe, kind of backwards from the normal thinking, but this is the game. So now this looks like 1 over 1 minus u, where u is negative x squared. And the negative is on the outside of the square, right? Like it's not negative x squared, it's the negative of x squared. So by the geometric series trick, this is equal to sigma n from 0 to infinity, negative x squared to the n. All right, you see what I'm doing? I'm just substituting into that formula. 1 over 1 minus blue is sigma blue to the n. That's the geometric series trick. Now we want to clean this up. Just 1 second. All right, we're back. So by taking this expression and plugging in negative x squared for u I get sigma n from 0 to infinity, negative x squared to the n. And I do that because I'm able to write my function as 1 over 1 minus negative x squared, which fits this shape. So I can replace it by this, and now we just clean it up. Negative x squared to the n is negative 1 times x squared, like that, sorry, all to the n. And that is sigma n from 0 to infinity, negative 1 to the n times x squared to the n, which is x to the 2n, like this. So this is the power series representation for this function. That's it. We are interested most of the time in the interval of convergence. So we can say here, and this is true, provided the absolute value of u is less than 1. And here u is negative x squared. So this is the absolute value of negative x squared is less than 1. When you take the absolute value, this negative is going to go away. And remember, the square here can pop out. So you get the absolute value of x squared is less than 1. You can take square roots on both sides. The square root of 1 is just 1. Here, everything is positive. We don't have to worry about plus and minus. And then you can unpack. So when you unpack, you find the same interval of convergence that you did for the original geometric series, 1 over 1 minus x. We haven't altered that at all. Technically, again, you should check endpoints, right? Because that's how we do this. We always test our endpoints. If you plug positive 1 in here, then this becomes sigma negative 1 to the n, which we know is a divergent series by TFD. If you plug negative 1 in here, negative 1 to the 2n is again just 1. So this same series at both sides. On a test, you would be required to check the endpoints explicitly. But I'm not, well, I can pay lip service to it here, right? So at x equals negative 1, here we're texting endpoints. We get sigma negative 1 to the n times negative 1 to the 2n summed from 0 to infinity. And since negative 1 to the 2n is an even power of negative 1, it's always just 1. So this is sigma n from 0 to infinity, negative 1 to the n, which we discussed diverges by the test for obvious divergence. And the same thing happens at x equals positive 1. That's the easier guy, actually. This would be negative 1 to the n times 1 to the 2n, which is equal to this thing. So again, diverges by TFD. So we found the power series representation for our function. Kind of this piece here would be our answer. And then we would need to also state the radius and interval of convergence, the IOC up here. The IOC is negative 1 to 1, including neither endpoint, because the series diverges at both endpoints. So the IOC here is the open interval from negative 1 to 1. The center again is 0. So this is what that IOC looks like. That means that your radius of convergence has to be 1 again. So if the question is, find the power series, what is the power series? Here's the power series. Oftentimes, they'll also ask you to find the interval of convergence and the radius of convergence. And for these guys where you're just using the geometric series trick, like we did here, you can always get there just by doing this inequality. No need for ratio tests, no need for root test or anything fancy. To find the IOC for your geometric series trick power series, just start with this fact. series will converge if the absolute value of u, which is the thing you're using here, is less than 1. And solve that inequality and test the endpoints. I'll give you some tricks to speed up the endpoint thing a little bit later. Before I do that, though, more examples are necessary. So again, we're going to find a power series and both the IOC, ROC, interval and radius of convergence for the function, let's call it f of x equals 1 over 3 minus x. Again, the geometric series trick is our friend. But again, it doesn't quite fit the mold. So remember the trick. Is that 1 over 1 minus is equal to sigma n from 0 to infinity to the n. So the problem is the 3, right? I have 1 over 3 minus x instead of 1 over 1 minus x. I need to rewrite this somehow to get rid of the 3 in that position. I need a 1 here and a 1 here. Again, it's algebra tricks. If you force factor a 3 from the bottom, force factor means factor it out even though it doesn't want to go, because there isn't a common factor of 3 here. If I force factor out a 3, this piece would become a 1. The minus stays a minus, and x will become x over 3. Take a second, make sure you see why. If we redistribute the 3, 3 times 1 is 3. 3 times x over 3 is x. So yeah, this is equal to this. And this might not look like it right away, but it is closer to this. Because now I've got 1 over 3 times some shit. That's 1/3 times 1 over that shit. Remember, fractions are grouping symbols. Top and bottom of every fraction is secretly in parentheses. So this really is the same as this. And now here is my u. Good old-fashioned x over 3. The 1/3 out front comes along for the ride. So I get 1/3 times sigma n from 0 to infinity x over 3 to the n. And like before, we need to clean this up. This isn't looking like a normal power series yet, right? It doesn't look like Cn times x to the n or Cn times x minus a to the n. It doesn't have that correct shape yet because this hasn't been simplified. This is 1/3 times sigma n from 0 to infinity x over 3 to the n is x to the n over 3 to the n. Which is 1/3 sigma n from 0 to infinity 1 over 3 to the n times x to the n. So at this stage, you can see your center. Your center is 0 because x to the n is just x minus 0 to the n. But before we call it a day, this constant multiple out front, he can come inside. I don't want shit out here. I want it all in here. So this is sigma n from 0 to infinity 1/3 times 1/3 to the n. I'll write it out like this, just this once, times x to the n. And when you multiply those two fractions there, you get 1 over 3 to the n plus 1. Times x to the n. And so sorry, here I underlined on the previous problem the u piece in each there. There it is. So this is the power series for this function. Good news, power series are actually unique. If you pick a center, then there's a unique power series for that function. It's very, very cool. So there is no other power series centered at 0 that converges to this guy. So not only does this trick work to find a representation, it works to find the representation, and that's hot shit. Again, we need to talk about the interval of convergence. So this is true, provided, again, that the absolute value of u is less than 1, which here means the absolute value of x over 3 is less than 1, because that's what we're using for u. Which means here you can split this up as the absolute value of x over the absolute value of 3, which is 3. And then you can multiply the 3 over, you get abs x is less than 3. At this stage, this number is your radius of convergence. But even if you don't see that yet, the last thing we do here is unpack. So I get -3 is less than x is less than 3. So my IOC, again, we're centered at 0 because x to the n, not like x minus 1 to the n, which would be centered at 1, or x plus 2 to the n, which would be centered at -2. Here we just have x to the n, so our center is 0. And this time I'm allowed to walk all the way out to 3, or all the way out to -3, and remain in my interval of convergence. All right, so the first trick I promised, I said I'm going to teach you some tricks to speed up the IOC shit. If you just use the geometric series trick, not only can you just solve this inequality, the series will always diverge at the endpoints. If you do anything other than the geometric series trick, I'm going to be showing you extra shit you can do. That's not true. Integrate or differentiate, I'm going to show you that. It's not true anymore. But here, because the series really is geometric, we really do know it only converges if the absolute value of the common ratio is less than 1. And that really does mean x has to be strictly between -3 and 3. So the IOC here really is the open interval from -3 to 3. And we don't actually need to test the endpoints. It's not going to hold later. Like I said, integrate the series, differentiate the series, use something else to get the series. Got to test the endpoints. If I just give you a series, got to test the endpoints. But if you cook up the series using nothing but the geometric series trick and algebra, then you don't need to explicitly test the endpoints, just solve the inequality. All right, that's trick 1. Speeding up things, trick 1. I'll give you some others. I'm going to hold here just for a second. Okay. So the radius of convergence, I should say also here, the radius of convergence distance from either endpoint to the center is 3 here. All right. So we've talked a big game. We can find some power series representations by plugging into the 1/1 minus x formula, 1/1 minus u formula. I want to present a challenge, and it's going to lead to a theorem. I'll find a power series for f of x equals the inverse tangent of x. I've dropped this one in the past, but I'm going to show you where it comes from now. Good shit. Here we're going to use the geometric series trick, but we're also going to use something else. Recall from our first example today, that 1/1 plus x squared can be represented as a power series as sigma n from 0 to infinity, -1 to the n, x to the 2n. This is true provided x is coming from the open interval -1 to 1. That was our IOC. What's the relationship between 1 over 1 plus x squared and the inverse tangent of x? There's two ways to say it. If I integrate this, the integral of 1 over 1 plus x squared is the inverse tangent function, arctan of x. You could also say if I differentiate this, I get this. Either way. But what we need to do is integrate, because we're going to go from a series we know to something we don't know. And in order to apply a calculus operator and go from 1 over 1 plus x squared to the inverse tangent of x, you need to anti-differentiate. So I know that the inverse tangent of x plus c is equal to the integral of 1 over 1 plus x squared dx, kind of thinking backwards. This is a fact. We know this. This is something you've known since the end of Calc 1. But now I can perform the integral over here as the integral of this power series. And this is where shit gets really good. This is the integral of sigma n from 0 to infinity, -1 to the n, x to the 2n dx. Because this function is equal to this power series. That's what we discovered at the start of class. As long as x is Fraternarian, this function is equal to this power series. So the integral of this function is equal to the integral of that power series. And the big deal is the integral and the sum talk to each other. You can flip them over. In fact, you can push them all the way in here. The only thing you're integrating are the x's. Right? That's the idea. So this guy, the integral here, only talks to the x. He only does anything to the x. The series and the integral, you can speak through one to something inside. You can integrate through the series. If you integrate through the series, -1 to the n doesn't have any x's in it. With respect to the dx integral, -1 to the n is a constant. You're just chilling. X to the 2n though, that's not a constant. That has an x in it. And the way I integrate a power of x is by adding 1 to that power and dividing by the new power. This is where we get our power series for arctan. There's still this matter of plus c to deal with here. So what we get, therefore, the inverse tangent of x plus some constant is equal to sigma n from 0 to infinity. I'll write this in the normal way. That's -1 to the n over 2n plus 1 times x to the 2n plus 1. And we can solve for c. It turns out to be 0. Remember, this is just a shorthand. We'll write it out. We're going to solve for c here. And the way you do this is by writing out the series. The very first term of the series is -1 to the 0 over 1 times x to the 1. That's x. Then when n is 1, you get -1/3 x cubed. Then when n is 2, you get +1/5 x to the 5. And then -1/7 x to the 7, and so on. Thus, when x equals 0, we have, and we know 0 is in the interval of convergence because My original interval of convergence is -1 to 1. This is a series centered at 0. Center is always in the IOC because the IOC is always symmetric about the center. We can plug in 0, and when we do that, we get the inverse tangent of 0 plus c is equal to 0 minus 1/3 times 0 cubed plus 1/5 times 0 to the 5 minus 1/7 times 0 to the 7, and so on. And literally every term over here is 0. You need to write it out like this, because if there's a constant term, you won't catch it. Please don't go plugging 0 into this sort of expression. Write it out first. There will be a problem on the test that checks to see if you understand this. Write out the series, then plug in the center. Plug in that same number over here. The inverse tangent of 0 is 0. So you get 0 plus c equals all these terms over here are 0, that's 0. So 0 plus c equals 0, that means c is itself 0 as promised. And we learn that the inverse tangent of x can be written as a power series. Sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1. This is one of those holy grail things again. Just like the geometric series, 1 over 1 minus u. This is something that you need to remember forever and ever and ever. Amen. Arctangent is one of those super duper important functions, shows up everywhere. This is one of those most important power series. We'll use it a lot. We'll use it as a starting point for problems down the road. The next section is all about that. So this, you need to commit this to memory, but you also need to get comfy with this process. So the next thing I'm going to do, if I zoom out and let you look at this for just a second. Next thing I'm going to do is kind of formalize this process for you. I'm going to show you what it is we did here as a theorem, how to integrate and how to differentiate power series. Take a second, write down any questions you have. I will have an office hour today. It may be later than normal. I'll post announcements letting you know. It all depends on how long this jury duty shift goes. And down here we solve for C. And that C was 0. Okay. So what the hell did I do there? Well, I integrated a power series. How did I do that? I treated it like a polynomial. Remember, we keep saying power series are just infinitely long polynomials. So here's the theorem. Integration and differentiation of power series. All right. A couple ways to say this. If f of x can be written as a power series, sigma n from 0 to infinity, Cn times x minus a to the n, so the series centered at 0, or sorry, centered at a, then the integral of f of x dx is equal to some constant plus sigma n from 0 to infinity, Cn times, and then you just integrate the x minus a to the n piece. That's the idea. And that will give you 1 over n plus 1 times x minus a to the n plus 1. And you can also differentiate these series like you differentiate polynomials. The derivative ddx of f of x would be Before I write this down, let me write out the first few terms of the series. The original series is C0 plus C1 times x minus a plus C2 times x minus a squared, and so on. When we integrate, we pick up a new constant. This piece would have become C0 times x minus a, or C0 times x, depending on your center. This piece would become C1 over 2 times x minus a squared, and so on. When you integrate, you pick up a new constant. That's this guy. When you differentiate, you lose a constant. So if I differentiate this series, which is what I'm trying to do, the derivative of f of x is that series. If I differentiate that series, this constant term, this little motherfucker right here, he's going to die. He doesn't have any x's. He really is a constant term. He's the term associated with n equals 0. So when you differentiate a power series, if that power series has a constant term, the starting index jumps up by 1. Everything else looks how you think it looks. If you differentiate an expression like this, some constant times x minus a to the n, the constant multiple comes along for the ride. You get n times x minus a to the n minus 1. Please be good, Bob. All right. This is the result. Two other things. If the original series has radius of convergence, not interval, but radius of convergence equal to r, then so do the integrated and differentiated power series. Another way to say this is integrating or differentiating a power series cannot change the radius of convergence. Can change the interval of convergence, though. Integrating, you can pick up one or both endpoints. That you don't necessarily pick up anything, but it's possible that you pick up one or both endpoints. Look back at the problem we just did. The radius of convergence for this power series is still going to come out to 1, but the interval of convergence is the closed interval from -1 to 1. Check. Okay. We should actually add this here. The IOC, you do need to check this. Check it with the ratio test. Check it by testing endpoints. You can trust me that the radius doesn't change if you want to. But the IOC here is -1 to 1 closed, right? R is still 1. The center is still 0. But the thing we integrated to get it had an open IOC. So we picked up both endpoints. It's just a fact. You can check it with the ratio test and by testing endpoints, like I said. So when you integrate, it's possible that you pick up one or both endpoints. It's also possible that you don't pick up jack shit, but you'll never lose an endpoint by integrating. Conversely, differentiating, you can lose one or both endpoints. I mean, the obvious example would be to just differentiate the arctan series. You know that that's going to be the 1 over 1 plus x squared series, and we know that that has an open IOC, but it can happen more ways. So, big results on integration and differentiation of power series. Basically, you ignore the capital sigma, you ignore anything with ends, you ignore anything that is only ends. you integrate just the x term. And similarly, to differentiate, you ignore the capital sigma. You differentiate only the x term. So let me show you some examples. I actually don't remember what time I started this recording at, so I'm not sure if I'm going over yet, but I suspect that I'm close. Today's a 50-minute day, so I'll do one more example and then I'll let you guys go. One of your harder homework problems looks like this. There is a new homework today. So we're going to find a power series for 1 over 1 plus x quantity squared. First, a comment. One over parentheses 1 plus x quantity squared is sure as hell not the same as 1 over 1 plus x squared without the parens. All right, those are not the same. You cannot use this series here. But there is something which is true. F of x here, 1 over 1 plus x all squared, that is 1 plus x to the negative 2. And follow me carefully here. This looks similar to the derivative of 1 over 1 plus x, which, you know, the original guy, that 1 over 1 plus x is 1 plus x to the negative 1, right? If you were to differentiate this, you'd get something like this. So I'm going to check and see what is the derivative of 1 over 1 plus x. Well, that's the derivative of 1 plus x to the negative first power, which would be negative 1 times 1 plus x to the negative second times the derivative of the inside here by the chino, which is 1. All right, if this was a 2x here, 1 over 1 plus 2x, that would be a 2. So what I get is negative 1 times 1 over 1 plus x quantity squared. Pause for a second, make sure you understand. I'm coming up with a guess. I'm saying this thing, my function, kind of looks like the derivative of something else. It looks like the derivative of this guy. So then I check, well, what is the derivative of that guy? It's this. So I'm off by a factor of negative 1. Therefore, divide both sides by negative 1, get rid of the negative 1. You get 1 over negative 1, just still negative 1, times d dx 1 over 1 plus x is equal to 1 over 1 plus x squared. But you see what I did? I just moved this negative 1 over here. I multiplied both sides by negative 1, or divided both sides by negative 1. It's the same shit. So my function, f of x, which is 1 over 1 plus x squared, is negative 1 times the derivative d dx of 1 over 1 plus x. Why is this good news? Because I know how to write this thing as a series. Side here, I know that 1 over 1 plus x is 1 over 1 minus negative x, which can be written using my geometric series trick as sigma n from 0 to infinity negative x to the n. So this thing is negative 1 times d dx. This thing is negative 1 times d dx of sigma n from 0 to infinity, negative x to the n. That's all. This function can be written as this series, right? I can put the parens back if it helps you see. This function can be rewritten as this series. So negative 1 times the derivative of that function is negative 1 times the derivative of that series. Now we simplify this and apply the differentiation theorem. So it's negative 1 times d dx of sigma n from 0 to infinity, negative 1 to the n, x to the n. You can still write your parens if you want. You don't need them for this. Now my differentiation theorem. Says, okay, you want to differentiate this function? Just differentiate the x pieces. So I'm going to differentiate this power series. Two things happen. This power series does have a constant term. The n equals 0 term is constant. Right? The very first term of the series is 1. It's 1 minus x plus x squared minus x cubed. So the starting index will bump up by 1. That happens only when you differentiate and only when the series you're differentiating has a constant term. The derivative ignores everything else, ignores the sigma, ignores the negative 1 to the n. But when it gets to this piece, it says, I know what to do with you. The derivative of x to the n, as it always has been, is n times x to the n minus 1. Now we can shuffle this negative 1 in. Negative 1 times something. This is a constant. It can come inside here. Negative 1 times negative 1 to the n is negative 1 to the n plus 1. So negative 1 to the n plus 1 times n times x to the n minus 1. That is your power series for this function. And remember, when it comes to the IOC stuff here, the thing we used for u was negative x. So absolute value of u is less than 1 means absolute value of negative x is less than 1. The absolute value of negative x is the same as the absolute value of x. So this is abs x is less than 1, which unpacks as negative 1 is less than x is less than 1. That gives me the interval of convergence for the series that I differentiated here. And when we differentiate, remember, going from here to here, where I actually took the derivative of the series, at most we can lose endpoints. So my IOC was the open interval negative 1 to 1. The series is centered at 0 again. The radius of convergence cannot change. So the radius of convergence for the finished series here is the same as for the series we started with. And since the interval of convergence was open, i.e. did not contain either endpoint at the start, when you differentiate, at worst, you can lose endpoints. Well, there's nothing to lose here. There are no endpoints in this interval already. So this is done. This is done. And the IOC for this new series is the same as the old one, negative 1 to 1. If I had integrated, then I could have gained an endpoint. If my original series had some endpoints in it and I differentiated, I could have lost some. But since the original series interval of convergence contained neither endpoint, The differentiated series can contain neither endpoint, because again, at most, when you differentiate, you can lose an endpoint. So the IOC and radius of convergence for the resulting series here are the same as the original. You can summarize it like this by saying 1 over 1 plus x quantity squared is sigma n from 1 to infinity, negative 1 to the n plus 1 times n x to the n minus 1. And there are two things about this that you may find unsettling, although it is just a fine answer. I want to be clear about this on the test. You give me this, I will be happy. But two things about this should bug you. This isn't x to the n anymore, it's x to the n minus 1. And the series doesn't start at 0 anymore, it starts at 1 because when we differentiated, we lost that n equals 0 term. And from here to here, we lost that n equals 0 term. You can do what's called an index shift to shift this back up. So we could also write this as 1 plus x quantity squared equals sigma n from 0 to infinity. What am I really doing? It's kind of like a u sub. I'm adjusting the starting index. And when I do that, that's going to change all the other n's in here. So like earlier, the first term had an n equals 1 here. So this n is going to become an n plus 1. This n plus 1 is going to become an n plus 2. This will be negative 1 to the n plus 2 times n plus 1. And then the x to the n minus 1 is going to become x to the n. Some people would consider this a prettier looking thing. Either one's fine with me. It happens to be the case that negative 1 to the n plus 2 is the same as negative 1 to the n. That can start getting a little bit confusing. I don't want to overwhelm you. So I will leave you here for today. All right, there is new homework up for you to look at, all having to do with this stuff, finding power series representations for functions. Some of it you'll be able to do now. Most of it, in fact, you should be able to do now, but we're going to look a lot more at this stuff on Thursday because it's one of those things that you just need a lot of practice with to get good at. All right, lads and ladies, that's it from me. If you want to talk to me about anything, I will have an office hour today. I cannot promise it'll be at the normal time. Obviously, I guess it's past that already, right? Because you guys are going to be watching this probably around 12:30. But yeah, that's it. So I'll post an announcement when I know how long the jury duty thing's going to last. I might be home by noon, who knows? But just in case. All right, take care, gang. If you need me, you can canvas message. Otherwise, I'll see you on Thursday.